So hello everyone, my name is Antoni Jaszcz. I'm from the Silesian University of Technology, and today I'll present an efficient Dijkstra-Based greedy algorithm for cycle route planning. The presentation will be divided into 5 parts, first being introduction, then problem, solution, result, and lastly conclusion. In the introduction, I'll briefly talk about graph theory and the terminology related to that. And when we have directed weighted graph, for example, we consider a graph where each edge has a weight assigned to it, as well as the direction. So we can, for example, traverse only one way through the edge. When we talk about walk in a graph, we talk about a sequence of connected vertices which we can traverse through. And the path is a unique walk, basically. So the set of vertices is unique. We don't go through the same vertex twice. And a cycle is a type of path which has the beginning and end in the same node. We'll also talk about cycle planar subgraph, which will try to basically design from a prior graph. And planar graph is a graph that can be embedded in a certain plane, for example, geographical one. And that there are no two edges that cross each other. So given the example on the right, we can design this specific cycle planar subgraph. And the measuring distance used in the experiments will be great circle distance, which basically takes into consideration the curvature of the Earth and is ever more so precise than the ordinary Euclidean distance, for example. And the problem at hand is finding a cycle with desired length and edge quality for designing a cycle route path. The data collected for the experiments comes from OpenStreetMap, which is a collaborative project, open source, and created and maintained by the community of mappers itself. And the OpenStreetMaps provides a useful API, which we use to create a graph representation of the real world data. And in this data, each edge has been assigned certain sets of attributes, such as length, or as displayed now, surface types. And this will be useful as we considered a certain bike profiles in our experiments. For example, mountain bike and racing bike, which the users of would like a certain quality of the surfaces to have. So, for example, with mountain bike, we would like to ride along more off-road type surfaces, while with racing bike, the more leveled and high-speed tracks are preferable. And the solution was to create a dedicated algorithm to tackle this problem. So the algorithm is based on finding smaller subroutes and attaching them one to another to create a full route. And the finding subroutes is based on the altered Dijkstra algorithm with cutoff distance. So we basically consider only nodes that are at a certain distance from the center, and then choose the best node to go to based on the scoring function presented right now. And in the main loop of the algorithm, we iterate through consecutive subroutes, and after finding each one, we check if we need to basically go back to the starting point if the length of the total route is, for example, too long. And we considered previously mentioned surface types with special weighting function, which basically acts as a multiplier for the length of each edge. So with favorable surface types, we basically consider the true length of the certain edge to be shorter as it really is, while with the opposite, we consider it as a longer than it really is. And the list of considered cases and settings is now presented on the presentation. To give you better view into the working of the algorithm itself, here is the short example. So beginning from the center point, we consider only the nodes at a certain distance from the starting node. And we choose the best fitting node to go to. Then in the second iteration, we now do the same, looking for nodes in the green area. But when choosing the best one, we also consider the distance from the previous node. And this is then repeated certain amount of times, to be exact, the n amount of times. And after each time, we check if the total length is not too long, if it falls within the estimated error. And if it is too long, we then backtrack our steps and try with the smaller distance to look for the best fitting node. And if the algorithm is satisfied, if the condition about length is met, then we have a complete cycle. And the results show that the best fitting number of the subroutes was 5, as any lower than that produce rectangular or triangular results, weirdly shaped, and the greater values produced edges crossing each other, which was also not desirable. And as for the numerical evaluation of the algorithm, we tested it on short and long routes against mean absolute percentage error. And in both cases, the result error was below the estimated maximum of 5%. And with the following examples, the impact of bicycle profile is shown. So when compared mountain bicycle to racing bicycle, we can see that with the mountain bicycle, the designed route was led through more secluded areas, more green areas, while racing bicycle was led through more urbanized areas with high-speed traffic. And the surface distribution can be also presented in the table. And unfortunately, there are limitations connected with the approach and the algorithm. The first two, insufficient and incorrect age labeling and extensive amount of possible surface types, is connected with how the OSM is designed. And we also had difficulties with finding routes in more secluded areas, which produced sparse or disconnected graphs. Assessing predictions was also difficult, as it mainly relies on the human immersion. So in conclusion, the algorithm performs well for the considered tasks and can easily adapt based on the chosen bicycle profile. It is also flexible enough to be easily adjusted to solve similar problems. And we plan to develop it further to address the aforementioned limitations. Thank you for your attention.